Okay, this is a talk. The contents of it may appear slightly disjointed because the actual work that went into it occurred over the last 2.5 years or something. So you should see the standard of Rust or the Rust functionality I'm using improve through the talk. But I will briefly explain what it was I was trying to do that led to this talk. So I've been working with computers, or playing with computers for a long time, from right back in, I guess, early 1980s, with the world famous Dragon 32 computer built in Wales, using BASIC then. A load of experimental, or not experimental, a progression of languages, including notable, or all the usual suspects like BASIC and Pascal, but interesting ones like Forth and APL, which have a rather different model to how you compose your instructions. And my working life, I guess, started back in the early 90s with things like Modular 2 as like the industrial version of Pascal. Actor was a fairly small, I think, interpreted object-oriented language with quite a Smalltalk-like environment that introduced me to OO concepts while I was at university, and then proper industrial work where people were actually paying me to do this stuff, which for the first 4 or 5 years was Fortran and C, and then later decades of Java and C++. And more recently, experimentally, I've been keeping an eye on things like F#, how does it differ, and Rust via this meetup and other means as these things have become more popular. I've always been slightly aware, despite it being my job, that I have no actual formal computer science training or qualifications behind me. I was a mathematician at university, but I have tried to keep abreast of what's going on and done plenty of exploring of my own over the years with sort of early design methodologies like the Jackson System Programming and Design methodology, which didn't really add a great deal, but it was my introduction to the fact that there were things like methodologies and later object-oriented. And probably the one that had the most effect on my actual work as an early team lead was extreme programming, but other ideas like test-driven development and design-driven development, and having 1 or 2 rather lengthy all-night sessions discussing lambda calculus with people who had done it at university and were trying to get across to me why it was so important. And as I mentioned, Rust more recently and some of the concepts it's introducing. So a lot of this led me, a few years ago, I came across references to books that would give me a broader idea of some of the ideas behind programming and computing, rather than all the procedural stuff that I use on a day-to-day basis. So this is a particularly well-known and recommended book, Structure and Interpretation of Computer Programs. It's been around quite a long time. It's quite scary how much apparently really advanced programming concepts was actually written about 40 years ago. And described. So this course, my brief recollection of it, this book was a compilation of the lectures they were giving about the theory of computer programming, and they didn't want to be distracted by the syntax of any language, so they used Lisp because it had as little syntax as possible. They weren't interested in that. They just wanted to talk about every aspect of programming they could. So I started reading this. It does cover a lot. Starts off with simple arithmetic and quickly into recursion and functions and having functions as arguments. It gets on to all sorts of data abstraction ideas. It does discuss, although you think of Lisp and functional languages as all being immutable, they do actually use it to discuss the topic of things like assignment and mutability, as well as getting on to concurrency, data, logic programming. So the whole of Prolog is quickly summarized and a working example produced as a Lisp program later on in the book, and even onto assemblers and compilers, still all just using Lisp. And I've got to say, the second half of that list, I've only skimmed to see what was in there to sort of look forward to, because I rapidly decided that to get the most out of reading it, I really needed to be interacting with the Lisp and the examples in a more practical way. And I could just download a Lisp interpreter and use that. But where would be the fun in that? At about the same time, I'd come across references to a book that used to be called The Little LISPer, more recently got renamed The Little LISPer. I apologize throughout this talk for jumping between calling things Lisp or Scheme. As of yet, I still don't know enough to even know what the difference is. And different ones seem appropriate at different times. If I'm referring to their book, it seems reasonable to use the name they've chosen for it, but otherwise I'll often talk about Lisp and Scheme interchangeably. This book was recommended, and I was delighted to get it through the post from Amazon and open it up to try to figure out what was so special about this tiny language, and discovered it was actually a fairly unusual way that they describe languages. Nothing like any other computer language book I'd come across previously. I know it's probably a little small, that photograph, but apart from the cartoon pictures, every single page of the entire book, which is probably 180 pages long, explaining the language, on the left-hand column of each page has little questions for you to come to an answer on. And on the right, it has often the very terse yes or no answer, and then a little message giving you an idea as to why that was the answer. It doesn't actually explain anything. It allows you to build up your sort of mental model of it. So again, I could just read this and try and make sense of it, and it all makes sense as you're reading each bit, but I was a bit concerned that unless I interacted with it properly and sort of forced myself to do the examples, I'd be missing things. So decided I would understand it better by writing an interpreter that I could type the questions into, and I want the interpreter to answer the questions for me one by one. At the same time, because of the work I'm involved in, we were looking at implementing an interpreter for languages. So I was more interested in more higher level ideas of parsing and interpreting. So reading books about that and learning Rust. So put all these things together, and the proper name for this talk should really be using Rust to learn to write an interpreter, to learn Scheme, to appreciate the structure and interpretation of computer programs. But I didn't think Alex and Chris would let me get away with that as the title for the talk. Even with that, to avoid analysis paralysis of spending all my time reading books and never getting actually around to writing anything, I decided I would do everything as simply as I could until I was forced to do something more sophisticated or advanced. I'd like to think that I've got enough decades of experience now that I could sit down and plan ahead and think what I'm going to need from a proper lexer and parser and interpreter, and could build a reasonably complex and complete one. But I didn't want to get ahead of myself and spend weeks doing that before I got back to the problem. So I wanted to just get stuck into the problem with as little a tool as possible. So I literally, because I was still early on in Rust, started with the Rust command line and a text file editor, although I did reasonably rapidly move on to Visual Studio Code so that I could more easily get it to run my tests. I won't go into the details of the system configuration because I know I've got to keep an eye on the time anyway. So to get started, the very first question, the first bit of text in the book is to give you an idea of the sorts of questions that appear in the little schema. The first question, is it true that this is an atom? And then it gives you an example of something, which in this case is just the word atom. And it informs us that yes, atom is an atom because atom is a string of characters beginning with the letter A. So we now have a basic idea. We've no idea of the motivation, but we now have a basic idea of what it is the book is talking about when it means an atom. Moving on, it gives one or two more examples to try and reinforce the idea. So Turkey is also similarly a string of characters. It doesn't add the extra little detail beginning with a letter. And it also mentions that numbers as a string of digits are also atoms. So we've got the sort of implicit idea that maybe if you've got a mixture of numbers and letters, then maybe that isn't an atom. There are many more questions in the book. I'm not going to go through all of them, but at this point, I wanted my computer to start answering the questions for me. So I wrote a little isAtom function that would take a text string, and I nice and brute forcefully went through the characters in that string, and if any of them weren't what it considered a character, which I simplified to just use the Rust method isASCII graphic, and I checked that we hadn't been told to. I should say that I'm reconstructing my history of learning from the commits that I've done a couple of hours at a time over the last 3 years. So at some point, I probably added in the nuance of looking for open bracket and deciding that that didn't count as a character. But that worked simply enough and allowed me to start writing some tests. I could use Rust's test mechanism, do some simple assertions to just check that my code is working. So as far as I'm concerned, each of these rows is similar to each of the questions that the book asks. You know, is atom an atom? Yes, it is. Is Turkey? It's 1492. Yes, they all are. Is an empty string? No, they're not. So this is more representative both of questions that are in the book and of extra ones that I added because I wanted to check various edge cases. Next question from the book. Is it true that this is a list? So it's the first time we've heard this terminology, but we get the idea that from the answer the book gives us, yes, it is, because the string is an atom. So anything that we've already defined as an atom enclosed by parentheses or brackets, a left bracket and a right bracket. So can I write a similar function? Yes, I can. It's again pretty brute force machine or state machine, just going around keeping some flags to check that we haven't broken the requirements for it being a list. Has it started with an open bracket? Have we found a closed bracket? It's by no means a perfect routine, and it does get better. You know, at the moment, my biggest challenges in Rust were actually the difference between strings and str or strut references. That was what I was wrestling with more than anything else. Other than that, I was using fairly basic constructs to actually get Rust to work and do what I wanted. There were little oddities that caught me out, things like you can end a function with a term in Rust and it's fine, it'll return that, but it doesn't like it if you try and do the same things within, say, an if statement. If I just had if and then a false, then it got unhappy. So it took me a bit of, well, I still haven't got 100% clear on when I can and can't use return, but I'm sure the model will become clearer to me. So I was able to write some more tests to get my computer to answer more of the book's questions about what counts as a list. Okay, moved on a bit more sophisticated to S-expressions, which sounds much more technical. So the book introduces them by clarifying that all atoms are S-expressions and all lists are S-expressions. And that's pretty much it. An S-expression is just something that's either an atom or a list. Bearing in mind that a list can contain other lists, not just atoms. So you can see it immediately gives you a sort of recursive structure. So it's very easy to write. I was still writing it pretty crudely, just experimenting with one mechanism after another. These all worked for the simple examples, but my crude parser for lists, for instance, because all it did was have a flag for the start and end of a list when it found the brackets, immediately started failing for nested lists. And I could have persevered and started doing counts and trying to check they were nested. But it all seemed like a very manual and procedural way to do it. And I wanted to start using the Rust language more rather than using the least amount of Rust possible. I wanted to start using some more of its techniques to make it stronger. I wanted to use Rust to stop me making mistakes, basically, in what I was writing. At this point, I wanted to start separating the text parsing from the processing of the things that we had parsed. which I knew enough from sort of flipping through early pages of text parsing books to recognize this as being a sensible separation of concerns. So I wasn't confusing the details, and I wanted to start using types. And, everything has been entirely string dependent so far, and wanted to start trying to enforce things rather than just relying on me doing it implicitly in the code. So introducing an enum for the different tokens that I was hoping to find is nice, because you get the sophisticated enums in Rust that allow you to have, for instance, an enum value of atom, which itself can carry data. So that worked nicely alongside the simpler open and close brackets, and write a simple tokenizer that could turn the string into a vector of tokens. Again, nothing too sophisticated, but already it's the separation of them being able to work with a collection of tokens and forget about strings meant I had one less lot of error processing to do. Still using mutable state at this point, so I was aware of and thinking there's probably better ways to do this, but plow on for now, because I want to get back to, I don't want to get too far away from answering questions. My tests, I continued to write unit tests to make sure that my tokenization was working, so I could pass in strings to it. And in the second example that you can see here, doing the tokenization. If the tokenization has worked, then checking the contents of the token, that it's actually picked up the value I want. So it was quite interesting working out how to write an assertion for something more sophisticated. In this case, embedding the match statement inside the assert seemed the easiest way. I could have just assigned it to another variable, but this seemed a reasonable approach to trying to keep my questions fairly terse, without getting them building them up too long. One thing I did discover to actually get even these simple tests to work was that I needed to use directives. They call directives, or they call macros. Anyway, to use the Rust directives to tell it that my token should support partial equality checks and to be debuggable before the tests would actually pass with me doing comparisons on them. I did check that all my that with my refactored version using the tokenization, all my previous tests all still pass. It's good to see. I'd been worried if I hadn't. By now, I had got everything working in Visual Studio Code rather than running it manually. I have, even now, sort of a year or two later on, I still haven't ever got around to getting the debugger hooked up for Rust in Visual Studio Code. I'm assured it's not actually that much effort, but to be honest, I haven't really found a need to do so yet. Either the examples I'm trying are too simple, but pretty much if it compiles, then it works, or if it gives me the wrong answer, it's pretty clear why not. Partly, I think I'm doing it in such small increments, but yeah, debugging seems a lot less necessary so far than I'm used to in C++. So the functions that I had earlier, I decoupled them, so so isAtom, for instance, no longer takes a string, which means that I have to now do things in 2 passes, turn my string into tokens, and then pass it to my isAtom function. This also allowed me to compose functions better. I could start having functions take tokens and return tokens, and have less error checking, because now I could rely on the types. I'd done one level of error checking in the string parsing. I no longer had to worry about anything because I had the correct types coming out. I also moved to test cases. So instead of having lengthy lists of asserts with all the extra, so here you can see each row has got the code, the is list, and the tokens mixed up with the test data that's varying line by line. Using Rust's test cases, I could then move just the data, or just the test data, if you like, into each of the test cases and separate out the code that's going to use that test data as a simple function, taking each test case and keep the code part at the bottom. So just to clarify, since we'll see quite a few of these examples, the test case I've got here, the first parameter is the sample Lisp expression that I want to evaluate. The second parameter is the result I'm expecting to get out. And the last part is the name of the test. Got to admit, I did find it slightly irksome having to come up with a unique name on every test case. I mean, it's good. I can understand why, and Rust does force you to use a different one. But a lot of the time, I didn't really need it. It has occurred to me since, having seen some of the talks that others in this group have done on macros, that I could probably fairly easily write my own macro that wraps test case that would extract the line number or something and use that as the message, which would have been sufficient, but I haven't had a go at that yet. Moving on, I started making things a bit more sophisticated. I'd been aware of tokens up till now, but I actually wanted to introduce S-expressions themselves as types. So write a function to be able to parse the tokens that I'm passing in. There's a limited amount of code I can fit on a slide, so obviously truncated it in some places, which is where you see ... but I tried to keep the interesting parts. In this particular function, this to expression, the main body is the second half, where it is looking at the top level of the tokens and matching the first parts against, is it an open bracket, in which case parse it as a list, is it a closed bracket, or is it an atom? So this is the very top level of the expression you've given it. If it is the start of a list, then I'm using a simple integer count into the tokens that I'm passing recursively into the sub function that is able to process lists. Internally within that, it has to go through the tokens as it finds them, looking for any sublists. And if it does, then it recursively calls itself. If they're not, then it adds on the atoms and slowly builds it up and returns back, hopefully returns back an S expression of what it's passed, where I think, I don't know if I included it in here. S expression is defined as being an atom or a list. Did I include that earlier? Yes, that was in the earlier slide when we had an enum. And an option, so it allows it to fail if you were getting stuff that didn't make any sense. I have found it slightly irksome in the parsing, and I sort of haven't, I don't know if it's deliberate, presumably it's a deliberate part of the Lisp language. It's been very carefully designed, and I think John McCarthy, the sort of designer of Lisp, has described it himself modestly as the most advanced computer programming language there is. But having the top level being forced to be a single atom or a list and nothing else has seemed to make the parsing slightly awkward. You end up with this top level part that is looking for that particular breakdown. It's got to be one or the other, and then it goes into the recursive looking at a list. It'd be quite nice if it feels like there's some repetition going on. Like I should be able to just consider the top level input as a list, unless it's only got a single item. But I'll put that down to me maybe not appreciating something yet, or not seeing a cleverer way to actually write my parsing of the tokens. If I move on slightly, I got an expanded version of the toList function, so you can see what it's doing. It's looping through the tokens, the current token. So it's still a crude for loop essentially, with current token, making sure it doesn't reach the end, incrementing until it gets to the close bracket, at which point it will be able to return out. So we've still got a single long list of tokens, and when we reach the matching close, we want to exit back out and give control back to the call-in function. So you can have multiple nested versions of the list. So you've still got the nesting inside it. This just gives you a little more idea about how the parts in it are working. You can see ultimately everything should come down to finding atoms at the bottom, unless it's an empty list. I was starting to have to play with boxes in Rust so that I could dynamically refer to these, which, if I remember rightly, I can't remember the details, but I'm sure it came up early on in one of our talks that when you were returning enums, they would need to be in a box because of their uncertain size, or possibly that was only when it was coming back from a lambda. I certainly needed to be using boxes at this point, although that does change in a little bit. If I move on. By now, I was getting a few questions that were getting in my way, or that were causing me to stop and think. For instance, it seemed natural that I wanted my function, if it's a toList function, then I know it's going to return a list. That's the only thing it's going to return. Maybe an option on a list, but it's only going to be a list. It's not going. I don't need the full generality of an S-expression. But you can't return something. Basically, you can't use an enum value as a type, which I guess isn't unreasonable, but because an enum value can carry data, it seems like it's halfway to being a type. So it seemed natural that I certainly tried to do it and it wouldn't let me. I realized since then that, okay, that's not really a problem. What I really want to return is the data within it. And if I really want to, then I could just create a new type and refer to that from inside the enum. So there's certainly ways around it, but I found it was intuitive to me to begin with that I should be able to return a type, and I had to think about, I can see why why it would be difficult or doesn't make sense, because it would only work for certain values within an enum and not others. So there clearly is a difference. They're not full types. Moving on, also because I've got a vector of what I was using for a box of S-expressions, because vector itself is on the heap, then it meant I didn't need the extra heap in direction of using boxes anyway. So I was able to simplify that code down a bit. I also started playing with Rust iterators rather than indexes, and that started to make things a bit nicer and safer using next to be able to traverse through the list of tokens. So I was learning more as I went along. I'm now all the way up to page 5 of the book, where they start to introduce a new function called car. And the question that the book poses is, what is the car of L, where L is a list. And it goes on to explain that the answer should be A, because A is the first atom of the list. So writing a car function as a standalone function, taking an S-expression is pretty trivial. If it's a list, then if it's not empty, then grab the first element of it and return that. So that might be a list, it might be an atom. If the S-expression we've passed in is not a list, then we pass back none, or the uninitialized or the failed value of an optional. So the optional isn't set, so we can check on that. And similarly, writing a test function for it was straightforward. Had to go through my palaver of creating a string, turn it into tokens, running my toExpression on it, and then you can see the actual work down here is actually calling my car function. So by now, I'm starting to realize this isn't a very efficient process if I'm having to write all this boilerplate to test each function as I'm adding it, and it's then quite painful to extract the bits to check their values are what I want. So I wrote a more general eval function to take an expression and started building things up. So this, again, this is a similar idea to what I was mentioning or complaining about earlier. I have a top level that has to worry about whether the thing that's coming in is a list or an atom. Then it moves on to the recursive evaluation of list. Whereas which in turn would have to then be checking for whether things are lists or atoms. In this case, the only thing we're matching so far is looking for the string car. So I'm checking if the first item of a list is the function name car, and then I call I advance the tokens onto the next part and call my car function on that next token as it comes in. So I'm getting the next token from the list, checking that it exists, and if so, then call in my car function on it, which should return the first value of the list. I was also starting to get a bit wary. I'm having to use clone more. Obviously, it was starting to complain that I was doing things that I weren't safe with references, and I was slightly loath to take too much time at this point trying to perfect it. I wasn't interested in performance, so I wasn't too worried about trying to make it as efficient as possible and always use references. I can't remember where I read some starting Rust advice is not to get too hung up on references and get it all working with clones if necessary, and then as you want to or as you're ready to, go back over it and start making things tighter. I'd imagine any more experienced Rust programmer will be fairly horrified at that, because by then you'll have baked in so many problems that it'll be really painful to try and retrofit by using references. But certainly for early experimentation, I was happy to go along with that idea. My test for it is now getting even deeper, and what I could see was that much as options are great and matching is great, it doesn't take your functions being very complicated before you're getting some quite deep nesting of your matches to actually pull out what you want and ending up with a whole even less pleasant tail of assertion of all the false failures for anything that isn't matching your primary case. I have improved, I'll move on rather than complicating things now. So by now I'm starting to get more questions. I'm still not happy with the fact that I'm looping over things, analyzing them, and want to start looking at things, or certainly want to think about replacing some of it with more recursion itself within the interpreter of the tokens. I did consider whether having the functions return none, and up till now the little schema book is quite adamant and clear on certain things, that certain functions, that they're not expected to work with certain types, that they are only defined for a list, or they're only defined for a non-empty list, or they're only defined for an atom. So an option seemed a good idea for anything that was incorrect, or potentially rather than none, possibly doing it as an additional S-expression, so actually returning an empty list or returning a nil value as an additional value. So that means the enum would grow by 1, but I'd remove the layer of options. The problem with that would be that the disadvantage now everywhere that is interested in, so instead of having to do a check on an option and then if that passes, then do the cases that I'm interested in, I guess I collapse it into doing one check on all the cases. But it does mean that everything that looks at an S expression now has to check for nil, whereas before I didn't. So I was slightly wary of that. It would have the advantage that if I returned an empty list, for instance, then many functions work with lists, so would hopefully work naturally with an empty list when it came out. But on the other hand, options did have the advantage in Rust that I could use the question mark operator to start chaining things together. But I was going to have to do something about this because individual test cases were painful to write. So I realized that I've already got something that parses a string and turns it into an S expression. It should actually be even simpler to write something that parses an S expression with its structure and types and turns it back into a string. And once I'd got that, then it was easy to put together tests where the result of the test of the evaluation should be a string, and I could write down what I expect that string to be. So now my test cases changed slightly with this test function to be in the Lisp string that I want to pass in, the string result that I want out, and the usual name of the test. And now the test case is just running through my process of taking the input string, turning it into tokens, calling my evaluation on it, turning the result back into a string, and then checking that it's equal to the expected string output. So suddenly I could move a lot faster because now I can concentrate on just adding stuff to eval, to cope with new functions, and adding more test cases to reflect the questions I was encountering. As I mentioned before, I was getting wary that clones were starting to creep in more and more, and that I may have to do something better with this at some point. But I was starting to use the question mark notation to simplify uses of options. So that was starting to make things a little bit cleaner and simpler. One of the results of me moving to my string rotation and tidying up the clones meant that I now actually fixed a bug, or without meaning to. It meant it was now impossible for the bug to exist. So now nested expressions worked. So if you remember, we've only added 2 functions so far. No, in fact, one function, car. So I can now apply nested versions of car on lists. So it'll pull out the first element of a list and then do it again, which could be a list itself, and then pull out the first element of that. So you can see in this case, the first case we've got here, the list being passed in has got 4 elements, several of which are lists of, in fact, lists of lists. And so the first element of the list is this list of hot dogs. So checking that all worked, and yeah, you can have a nested version where you're calling get the first item of this list. I'm just trying to work out if I've aligned the brackets up properly. That should return a list the same as the one above, and then so an extra call of car on top of that should return the first element of the list, which is indeed just still a list containing hot dogs. So nested ones were working, which I was most pleased with. On to all the way to page 6 now. Don't worry, I do not get through the whole book before you start panicking. The next function that the book asks about is CTR. I don't know if anyone else wants to butt in at this point with any suggestions on how this is supposed to be pronounced in Lisp circles. Kada, it seems a little awkward. Any suggestions?
You have it right.
Kada?
No, just Cutter.
Kada I can go with. I got to say, I'm sure there's a reason why they chose these particular names, and cons when we got onto it seems a bit more obvious as construct or something, but car and Kada seem odd and awkward choices when you could have called it head and tail, but I'm sure they had their reasons. Okay, moving on. We're introduced to the to Kada, and again, applying it to a list. The answer should be, in this case, another list containing all the elements apart from the first one, so the tail of the list. Interestingly, the book describes it as being the original list without car of the list. So it's already it's subtly nudging you to define functions in terms of functions you've already got. So we already knew that car-l would produce the first element of it, but they don't say that. They're just suggesting it's going to be the list without what you would have got from car-l. And also starting to give you bits of one element function potentially calling another. So it's quite a subtle book in its sort of Socratic teaching method of asking you questions and getting you to figure it out, and even the way it answers them. So again, to actually implement this function was only a tiny bit of code. Checks it's a list, checks it's not empty. If so, then I get to use the Rust function that allows me to take the remaining slice of the list and crudely dump that back into a vector and create a new list element containing it. My eval method already had car in it. I've now added coder, which does a very similar thing. It's still looking out, recognizing the string name, checking that I've got a next parameter to pass into it. It's making sure I evaluate the next the parameter. So I keep pointing at the one that's in my presenter view rather than the one on the screen. Make sure I evaluate the next parameter before I make use of it, and then pass, if that comes back with something valid, then pass that into coder to actually pull out the results. So it's this mechanism of calling eval on any of your parameters before calling the function that gets the nesting all working. More test cases from the book and extra ones of my own. I think most of these are from the book, making sure it is all working. There are sort of little nuances, like if it syntactically makes no sense, then rather than just crashing, I intercept a bad parse and send back a useful message for me during my testing. Everything else should be a valid result. Add on to another function, the cons function, basically allowing you to concatenate things together, which again, fairly straightforward to write. And now I'm starting to get a bit more sophisticated with my implementation of eval. So I've got from a block of code for each piece of text, I'm now doing a simple guarded match for each piece of text. And calling the function directly and making more use of the optional return values, but also the fact that my eval, I've now moved to being a member function of S-expression, or to be effectively what I would think of it in C++ terms as a member function of the type, rather than previously it had been a free function that I pass the S-expression into. I guess in recent years, I've become a lot more wary of member functions, because it's a very strong coupling. Free functions, if you can do the same thing with a free function and don't need access to the internals, it generally makes for easier code in C++, if your functions are semantically equivalent and it works over a wider variety of types. But if I want to use the question mark operator, then they need to be member functions to get the effect I wanted. And moving it into, certainly in this case, it's not causing me any problems, and it's starting to clean up the syntax a lot. But I was starting to experiment with different ways of doing things in Rust, and hopefully making better advantage of it, and the way options combine together quite nicely. You can see in cons the early evaluation of parameters I talked about before. I'm doing it on both parameters, both parameters that are going to be concatenated together. This does rely, because I'm doing the incrementing of the iterator, as well as the evaluation of it, to move move along the line of tokens. It does rely on the two parameters being passed into cons being evaluated in the order that they're written, which it's a while now, but I'm pretty sure I looked it up at the time, and that is well defined in Rust, though in C++ it's generally not guaranteed that your parameters are going to be, or was only recently, was it added to one of the recent C++ standards that they were going to fix the order of evaluation? I know they held off for a long time in case, because of compiler optimizations might take advantage of it. But anyway, in Rust, parameter evaluation order, I'm pretty sure, was defined and reliable, so I could use that. I'm aware I've been monologuing for quite a while, so I'll try and speed up a bit. More test cases to prove it works. Adding the null function. Lisp has a standard of putting question marks on the end of Boolean type functions. Null is for anything that's a list with nothing else inside it. So you can't apply it to atoms, which seems a bit of a pain. There are various functions. It seemed like if you just expanded them to apply to more things, that it would actually work more naturally than just declaring them to not be allowed to. Quote function, I can't remember the details. So far in the book, as far as it goes, all it does is return the same thing as the parameter, which doesn't have much immediate use. I have a feeling it becomes a lot more significant if it's, for instance, for avoiding early evaluation or something. Waiting to see how that develops. There's lots of things in the book where they ask you some questions about something, but not enough to fully understand it and get the impression they're going to come back to it with more nuances later. So I moved a few more of my functions into being member functions of S-expression, which tidied up the eval function a bit more. So now I've got this increasingly long list of question mark operators. The cons one is particularly interesting in that you've got both parameters, or you've got one parameter is now able to stream all the way on, but the second one still gets passed in as a single parameter. So rather than cons having two parameters, it's now a single parameter argument that can be a function that can be applied to an existing S expression. What was I trying to point out here? Yeah, so this is an idea. If for instance you expanded is null to allow other things than just lists, which the book does note in a comment that different dialects of Lisp or scheme allow certain things that others don't. In this case, it cleans up is null, because if it can take both an atom or a list, then suddenly is null can be applied to everything, and I don't need an optional because it's always going to work. Some more functions to add. Atom just checks whether the parameter is an atom, not a list. Equals is quite interesting, checking that the two parameters are both the same. Equals at this point in the book, it's quite adamant, only applies to atoms, which seems odd. It would be an ideal opportunity to have to recurse into checking that all the elements of two lists were identical. And lat, which stands for list of atoms, so strictly everything in the list has to be an atom, not a list, was the other function added. All fairly easy to write, but what the book at the end of chapter 1 now challenges is, can you write the lat function to check whether a list is a list of atoms using your existing functions? So rather than thinking of it as a standalone new thing, do it in terms of all the existing ones. And it's a tempting idea, because what we want to check is that the list L is not an atom, and that the first element of it is an atom, and that the remainder of it, or coda L, is also a list of atoms. So you're getting the idea of using recursion, but you also need additional ideas, like being able to define something, lat in this case. So the idea of creating functions, using recursion to call that from itself, and something that's able to start branching. So if it, so moving on to, so having given us the question and then pointed out that we can't do it yet, it jumps onto chapter 2 with the rather more formidable looking expression, define lat, lambda L, cond, and a bunch of conditions, and just poses the question, okay, what does this mean? There's no hint as to how we should read it or interpret it. It just, as is this book's want or standard, it just asks us, okay, given that, what is lat of L, where L is a small list, and tells us that the answer should be true. It does go on to expand a little bit more, explaining that how to break up the parts of it. So very briefly, because I'm aware we're getting close on time, the inner part, the cond function, can take as many arguments as you like. It expects each argument to be a pair or a list of 2 parameters, where the first parameter of each pair should evaluate to true or false, and the second parameter will be what cond will return if this first parameter evaluates to true. So in this case, if we call, in this case, if the list is, I'm not sure if I've actually missed out a letter, that might have been an is null question mark on L. It should have been, unless it's implicit. If the list is null, then we pass back true. Apparently that counts as a list of atoms. Or is the first element of the list an atom? And if that's the case, then check that the remainder of the list is also a list of atoms. So this was our intuition of what we were looking for, just with the edge cases added on. And for anything that fails to pass that, it should come back with false. So Lisp seems to have hash T and hash F as true and false. So that's how the condition part is supposed to work. If you evaluate it on its own, the lambda part is saying that we're creating, if you like, a function which can take one parameter, and when you get your one parameter that you want to apply your function to, then replace everything in this expression that has that name with the thing that's being passed in as the parameter. And lastly, the outer layer is defining, so it takes 2 parameters, a name for your new thing and the thing you want to be called by that name. So you can see they've introduced quite a lot in one go. They could have started off by doing define of one name to mean another name, for instance, but they clearly wanted to whet our appetites at the start of the chapter. So how did I get on? Well, I wanted to be able to write tests firstly for the cond statement, so it could work with multiple expressions. So I'm taking in the different parts, whether in this case A and B are equal. If that becomes true, then I return the string or the atom equal. Otherwise, I return not equal. Else, it was a suggested part of the, I don't know if you'd call it syntax. I can't remember how the book introduced it, whether it described, probably without much explanation, whether it described it as a part of the language or not. I cheated in my implementation, and just whenever we encountered the function or the symbol else, I just made sure that would evaluate to being true. So it would be exactly the same as just putting true as the last clause. But I wasn't entirely happy with that. Implementing the condition was quite nice. Passing the iterators in meant I could start playing with, so this used a Rust algorithm, or well, a function that takes a lambda at least. So I'm starting to get away from loops more and use some of the natural library facilities. So passing in my lambda of checking through the list of pairs to find the first one that would be true, and then it would return. Once I got my the first condition of my list of conditions that passed, I would pull out the second part of it and evaluate it. So that would actually find the results that I wanted from the first clause that would pass. What did I want to say in this? Oh yes, this is now then the next level up, working on trying to get define to work. Okay, for define to work, that means I've got to assign things that I'm reading to names. which meant I needed to start building up some sort of concept of an environment that I was going to be storing and keeping track of. So a simple one was just a hash map of the string names against the S-expressions that I was going to be assigning to them. What that does mean is that all of my functions need to be able to take advantage of this environment. So for instance, if they're going to have to look up a letter to replace with a different, an atom name to replace with a different atom name, then the evaluations need to be able to use that in a recursive manner. So I need to be able to start passing my environment into the evaluation and into any subsequent evaluations in a nested way. Define itself is very easy to add. It just takes the environment and inserts the new string and the remainder of it into the environment. And that led on to the interesting question of what should be returned from define. Up till now, everything I've done has been as a function that returns something. And to conveniently fit into my framework, this needed to return something. And I ummed and ahed a bit about it. I looked up a few things to see. I cheated. I didn't look ahead in the book yet, but I did a bit of Googling, and they described define as being a control structure, and it's not an expression. It doesn't return anything. But it seemed to me that if it did return things, it would simplify some aspects. It doesn't matter. I don't think it matters greatly, certainly at this stage for what I'm doing. So initially, for now, I just had it return the name of the what it was defining against, so that I could easily test that it was actually running properly. And later, I just changed my mind and decided I would return an empty list from a define instead. Far more exciting was I now got to the point where instead of having else inside the interpreter, so it was spotting the word else and interpreting it as meaning true, I could now do it inside my Lisp expression that I was submitting to my interpreter. So I could take some of my code out and actually do it in Lisp instead. What I would say is that this uses the idea of having one expression followed by another expression, which in turn means define returning something. I have no idea whether this is really the way you're supposed to do things one after another in Lisp. I have yet to find examples. All the examples and questions in the book are standalone one expression. But for what I wanted to test I could define something and that then subsequently I could use it. So in this case, I've defined else to be true. And then when I get to else, I want internally it to substitute the value I've defined for true and evaluate it when it's doing this cond analysis. And it did actually work. It successfully realized that A is not equal to B. So that first part doesn't pass. It realized that else means true. So this one does pass and gives me back the not equal. The true part here is because that's the value at this time that was being returned by my define statement. Although I said it returns the name, it actually seems to be returning the value. So I'm not sure if that's my typo in the slides, but you can get this side effect that all the elements of my sequence of expressions are all returning values. So more work to be done on that. Okay, next steps. I'm afraid that's as far as I've got in terms of implementing it. But at this point, I was then looking at lambdas and thinking about implementing the actual storage of a function to be able to call it. Maybe simplifying it to begin with and doing lambdas that don't capture the environment, so they just do simple calculations. But what was worrying me more was that the structure I've got was starting to feel a bit artificial and hacky, and there were a number of questions. Certainly lots of problems with my environment that I'd created. The whole thing was going to blow up if I had any cyclic lookups in it. Scoping wasn't really working, so things could exist. Once things went in there, they'd never come out of there, so things could exist much longer than they're intended to or expected to. it doesn't really cope with the idea that things might change their names. It would just overwrite them. There's significant cloning going on, and that was worrying me more and more. And I need to think more, understand more about define and how to cope with it. Should I deal with it differently from functions? Should I have it as a language structure in some way? By now, I was quite happy to to go back and say, okay, using what I've learned, what do I want to do? How do I rewrite parts of it? I'm not too worried about the parsing parts at the beginning, the string stuff at the beginning and end. It's the middle part that I'm interested in. I did want to now go back and start avoiding clone and also making more use of Rust to enforce me using references, because I'm not changing any of the inputs. All the inputs ultimately are strings that I should just be able to have a reference to that substring, and everything else just be references to lists of strings, or I shouldn't be having to clone things unless I'm actually creating a new layer of structure that's trying to contain the references. So I did feel that I should start over with more attention paid to that. I also wanted to store functions as function pointers, which I have not looked up in Rust to see how we do that. So for instance, the last version of eval that I had, you can see I've still got this forced mapping from strings to actually call in the functions, whereas what I'd like much more is to just be able to replace all of this sort of match sequence with a single lookup this in a dictionary or something, and run the function that's contained alongside it. So then as I was thinking more about it, I thought, well, actually a map probably isn't what I want. What would be quite nice is to think about things, particularly the environment, rather than as a growing list. Seeing as the whole point of Lisp and functional languages is to try and make things all be immutable, and that simplifies everything. If I kept my environment as an immutable list that kept growing, but would respect, as you go into a sub function, that would look at the environment as it is. So it would only know about the things that have been defined in the environment up to that point. And it could add additional things to it, but when you came back out of that function, those additional things wouldn't affect the calling environment. They'd only have what had been in the environment up to that point. That seemed to fit what we wanted from an environment much better, to treat it as a list, and to allow different scopes as they progressed to add different heads onto that list, which in turn was making me think, well, hang on, that sounds like we actually want to use a cons head tail list type structure internally to actually implement this parsing of Lisp, which is maybe indicative of the sort of idea you hear a lot about Lisp being self-hosting and implementing the interpreter for Lisp in Lisp. And I could start to see where this was sort of starting to come together. I was thinking maybe of splitting the whole process into 3 passes rather than 2. So one to tokenize it, and then maybe one that just worries about turning my flat list of tokens into a more structured list of lists of lists, etc. And then eval would know that it's only ever looking at a more meaningful list. So I wouldn't have quite the same issue having to pass back the iterator to the next part of the long list. And I was also, some of these, if I could remove some of the errors, if I could make it a bit more relaxed about what it would accept, then that would potentially remove some of the nesting of options. So for instance, if I had broken things down into a structure where I had a list of lists of lists, it'd be much easier to ignore any excess parameters. At the moment, it has to be correct because it's relying on the next thing being processed by the level above. So I had to be a lot more careful about them. It would be nice to get rid of that. Ambitions going forward, I want to see how many the functions can be defined within Scheme or Lisp. For instance, as I did with with else? Can I do it with other functions? Can they be defined inside there, so that you've only got the most fundamental constructs possible having to be described in Rust itself, and that everything else is done inside Scheme. I'm interested to, I sort of got the notion that you've got this sort of underlying computational machine that is the minimum of what you need, and then that can then do everything. I want to see how fewer constructs we actually need. I also started wondering, rather than the tests being inside or being in Rust, could I write the tests themselves in Lisp? So you can imagine your Lisp script being a load of definitions, and then writing your tests as being a call to that function with the input, and a call to equals to check that the result is equal to a particular string. To do that, maybe I need to think a bit about how this is supposed to be outputting its results. So more stuff to think about in the future, and boring stuff like it would be good if when there are problems, I actually stored a bit more information about where the error occurred, and starting to think about, well, my input scripts for each test are getting longer and longer. Do I want some sort of an include or import mechanism so that I'm not having to repeat stuff quite so much? And apologies if people were hoping I'd get a lot further into Lisp and how to use it, but I'm well aware I've only scratched the surface of the basic syntax of Lisp. I've learned plenty in that time, and there's an awful lot more to do with Lisp to explore, and I've got nowhere near even getting any appreciation of what macros are in Lisp, which is often described as the icing on the cake, or the most powerful part of the machinery there. But I've got plenty to look forward to. Sorry for taking so long. I'm more than happy to answer anything anyone's interested in.
Hey, Richard. I've got some good news. Let me put my camera on. I've got some good news and some bad news for you. The good news is that I can see you slowly converging and understanding Lisp. But the bad news is you're doing it the really hard way. and that's not your fault. I think the fault is the book you're following. Lisp is extremely simple. Scheme is even simpler. And the best way to teach it is from the top down. Unfortunately, the book you're reading is teaching it from the bottom up. And so it isn't obvious when you do that what the concepts of Lisp and Scheme and how they work are.
Yep.
Now, I'm going to answer quite a few of your questions you have as quickly as possible to give other people a chance to talk to you and ask questions. Or I could just leave it to the end, and it's up to you guys. Let other people have a chance. But I can talk. I can easily describe how macros work. What's the difference between macros and lambdas? I can talk about how to handle errors. I can talk about how to make your life a lot easier by understanding what REPL means, and the fact that the term REPL actually comes from Lisp, and REPL is the clue in how you implement a Lisp interpreter. You literally is read, evaluate, print, and loop. You read a stream of tokens, which comes from a stream of strings. But there's also, you can also do some read mapping, so you can transform tokens into new tokens as part of Lisp. But that's more of an advanced thing. But essentially, it dissolves your is it S-expression or atom when you're doing it. Basically, all the read does is give me the next S-expression.
Yep.
From an input stream, and if the input stream is empty, then it asks the user for input.
Okay, so this sounds like this answers my question about how do you do a sequence of expressions. This is it. Basically, your
exactly.
read reads the first S expression, you work on that, and then you loop, i.e. go to the next one.
Yep, that's exactly how it works. And if you understood that from the beginning, it would have been a lot more obvious to you, I think, about how Lisp works. The evaluate is essentially take the S expression and evaluate it, and depending on the on the type, it evaluates in different ways. So a symbol will evaluate to its value in the environment. a number will evaluate to itself. A list will evaluate by taking the first element and evaluating that, and based on that type, you do certain things. This is how you differentiate between macros and functions and primitives.
Yep.
The main difference between macros and functions in Lisp is that in a normal lambda, you evaluate all the arguments, but in a macro, you don't evaluate the arguments. You just pass them as is into a normal function, and then the macro can choose to evaluate them or not, which is very important for stuff like if.
Yep.
And because you want to evaluate both parts of the if, and then it returns a S expression, which is then inserted into as your next thing to evaluate.
So typical parameters for functions are all evaluated immediately, not
yes.
lazy, whereas macro ones are lazily evaluated.
Yes. So given a list, you take a look
yep.
at the first atom, or you evaluate. You get the type of that, and if it's a symbol,
yep.
You evaluate that, and if that's a function object or a primitive, or you then evaluate the rest of the terms, and then.
So does that mean cond is a macro, not a function?
Cond is a macro, yes.
Yeah.
Well, it's probably more like a primitive, but a macro is tend to like use define, where you actually use Lisp to define it. Where cond is more like primitive, but primitives are macro-like. I forget what the actual name for them are. There is an actual name for what they are. Perhaps someone else can say. But anyway, I could talk more about concells. I could talk about how to improve the environment. I could talk about how you handle errors in Lisp, where you don't even have to worry about errors.
What I'd like to do, I'd half like to hear a lot more, but I'd half also like to figure out more on my own. But what I would like to do,
I'll say no more. But try to look at Lisp from the top down. Deal with the REPL. And go from there.
What I might do, if you're okay, is contact you, or if you want to contact me on my email, just with your email, and I might ping you with questions. Oh, excellent.
I'm on Rusty Plus. You can find me there. You can send me a direct message anytime. I'll be happy to help. I've written a Lisp interpreter, and I've even called Nerd, and that was a C++, and I've been thinking about writing a Rust for a long time. But anyway, I give other people a chance to talk now.
Appreciate all that, Matt. Thanks. Any other thoughts from folks? We got a good number of people joining or applying or RSVPing for the meeting. So clearly there's something successfully clickbaity about the title we put out.
I feel like I've just lengthened my reading list by a lot, but I don't have questions right now.
Possibly don't read them in the same order that I started. It would be Matt's advice. There's far more sort of normal computer languagey explanation-y books, like the Common Lisp book is a much more, probably more straightforward way of describing the language.
A really good source. I'm going to link it on the chat now. It's called Scheme from Scratch, and this guy just basically writes a scheme from scratch, adding feature after feature, and really explaining. And that's a really good resource if you want to look at it.
Yep, thank you.
I can quickly mention the difference between Lisp and Scheme if you want.
Yep.
And they are very different. Common Lisp, rather was actually Common Lisp and Scheme. So the things I can think of off the top of my head, Scheme is called a Type 1 Lisp, and Common Lisp is called a Type 2 Lisp. The reason for that is that Scheme has one namespace, and Common Lisp has two namespace. That is, it puts function names in a different namespace to every other symbol. You need a special sort of syntax to actually access a function name. Also, Scheme has tail recursion built in. If you return a value tail recursion optimization. So
Yeah.
recursion just convert to iteration at that point. Also, Scheme has static scoping, which is more akin to what you're more used to with C++, Rust, and so forth. Whereas Common Lisp has what's called dynamic scoping, where it can variables aren't necessarily local in scope. You can change outside variables and stuff. And I think it's horrible. Personally, I prefer Scheme's way of doing it. But to get revenge, Scheme does not equate nil and an empty list. In Common Lisp, nil and an empty list are the same thing, and I think that's a more elegant thing, because a lot of things just fall out much nicer.
Yeah,
because you can return nil, and whereas Scheme makes that a little bit more awkward.
Yeah. Thanks for that distinction. Other folks, I'm aware we're late for time.
Thank you very much, Richard. That was a great talk. Is there any final questions quickly for Richard?
Will you be doing another talk on the next chapter of schema?
On past experience, we might need another pandemic, and I wouldn't want to wish that on us, just so that I could get a bit of time to work on it. But yeah, I'm quite excited to actually have another pass now with improved understanding and comprehension and ideas, and I had to forcibly stop myself thinking about them, because I want to do this talk on my thoughts and feelings up to this point without sort of getting distracted by nicer ways to do it. But yeah, if I make a chunk of headway, particularly if it's sufficiently relevant to Rust, then I will be more than happy to do a sequel in a while.
I've also written a fourth as well, Richard, if you want to talk about that. I love fourth.
It is a pretty nice minimal language.
It's amazing.
Cool. Thank you very much. So just an outline of the talks that we got coming up. So the next talk is going to be about Cargo Expand. Kira is going to be leading that conversation. That might be on the 10th of August. And then after that, we've got Concept and Traits. And Alex is going to be doing that presentation. So that's going to be potentially the 17th of August. Now, those dates are kind of subject to change. But that's kind of what we're looking at. There is the traditional after party now over at Discord. If anybody wants to go over to Discord and talk or chat or anything like that over at Discord, that'd be taking part now. I'm going to watch some football. So
I'd love to join you, but I've been keeping my wife waited long enough for dinner.
Yeah, I'm currently on holiday, so I'm also going to bow out. But thank you. That was great.
But Matt, I do appreciate all your insights, and hope to come back to you on it.
Oh no, thanks for the talk, Richard. It brought back some happy memories of working with Lisp, which I haven't thought about for a while. So I appreciate that.
My pleasure. All right, folks. Bye for now.